Okay, an end behavior model. So for really large values of x, we can sometimes model the behavior of a complicated function by a simpler one that acts virtually the same way. Okay? Give you an example. Say we've got the polynomial function 3x to the fifth plus 2x to the fourth minus x to the third plus 2x squared minus x minus 7. In pre-calculus, we talked about the end behavior of polynomials. An end behavior basically is what's happening to the function as x gets really, really large or really, really negative. And what we found was the only term in a polynomial that really determines that is the first one, right? Because the power is the largest here. It's kind of like we talked about, as x gets really, really large, this thing's going to blow up huge. These are all going to be pretty big too, but nothing in comparison to this first one. So if we're looking at end behavior, really big values of x, really large negative values of x, the only term that really shows you what's going to happen is this. So our end behavior model for f of x is 3x to the fifth. Because that function, just that first term by itself, does virtually the same thing as the entire big one as x gets really, really large. Okay? So the end behavior model for this f of x would be this other function, g of x equals 3x to the fifth. All right? It's pretty straightforward because you always just steal the first leading term, whatever it is. Other functions have end behavior models too, not just polynomials. And so it's not always easy to come up with what those are, okay, but there is a way that you can kind of test to see if what you've chosen is going to make a good end behavior model or not. And there's both right and left end behavior models. A right end behavior model would be as x goes to infinity. A left end behavior model is as x goes to negative infinity. So sometimes it's the same function for both. Sometimes it's different. Just kind of depends. So here's the definition, though, for both of those. So a right, and we'll just refer to them as EBMs. So a right EBM So a right end behavior model for f of x is the function g of x if the limit as x goes to infinity of f of x over g of x equals 1. So if you take the original function, divide it by the one you think is a good end behavior model, and that comes out to 1, it'll work. Now take a look at the one we just talked about up here. If I were to take this entire big, huge polynomial, divide it by 3x to the fifth, and I did the limit as x goes to infinity of that, do you see how that's going to come out to 1 yet? It's a fraction, right? The degree on top and the degree on the bottom would be the same. And what do you do if they're the same? You take the coefficients of the leading terms and divide. What would be the coefficients of the leading terms? 3 and 3. And what do you get when you divide 3 by 3? 1. So it works. So it's an effective end behavior model because the limit comes out to 1 the way we want it to. Okay? The left end behavior model, same thing, except it's the limit as x goes to negative infinity should come out to 1. Okay? So let's jot that one down here too. So that one also should come out to 1. And we can test that out with this one too. It would work the same way. Okay, just thinking about x going to negative infinity, 3x to the 5th would work in that case too. Yes? For polynomials, stealing the first term always works. But like I said, we're not always looking at just polynomials, though. So I'll give you an example. We'll do one of these. We got a little bit of time left. So let's say we want to look at f of x equals x plus e to the negative x. And I want to come up with a right end behavior model and a left end behavior model for this one. A simpler function that behaves the same way as this one does when we get really, really large with x. Okay? And I can't just steal the first term for this one and know that that's going to work, because it's not polynomial anymore. It's this exponential type thing going on. Okay? So, if you have something like this, it's kind of a guess and check game, which kind of stinks because you don't always know where to start. If you have something like this one, where you've got two terms added together, testing out each individual term first is a good place to start. So let's just look at x and see if x works out for us. Okay? So our guess, we're going to go with g of x equals x. We're going to make that limit and just see what happens. Do we get something that works out? So using that, the limit as x approaches infinity, we want to go f of x over g of x. So x plus e to the negative x over x. And we want to try and see, can we simplify that, get an answer? And if so, is it coming out to 1 or not? So this I can break apart. So that's going to be the limit as x goes to infinity of x over x would be 1. And then I'd get e to the negative x over x. Yeah. If you have a function that has two things added together, a good guess is picking one of these two things. So I'm just starting with x, just to see what happens. Okay, so when I put that in here, I got 1 plus this. Well, let's think about what we know this is just 1, but we're hoping this comes out to 0, right? Because then we're good. So if we put in infinity here, e to the negative infinity, think about what a negative exponent really is. It would mean it's in the denominator. So e to the negative x is really 1 over e to the x. Okay? And if I plug in an infinity, well, what's e to the infinity? Something raised to the infinity power? It's going to just keep getting bigger, right? So that would be infinity. So what I'm looking at here is, maybe this will be an easier way because I feel like I'm losing you here a little bit. Think of it this way. E to the negative x is 1 over e to the x. So it's really one big fraction with e to the x shoved down in the bottom. Okay? As x goes to infinity, what's going to happen to this denominator as x goes to infinity? It's going to just keep getting bigger, right? So what's going to happen to the whole fraction? It's going to get smaller, go closer and closer and closer to 0. Okay? So what we've got here then is 1 plus 0, which equals 1. We got it. We found the right end behavior model for this one. Okay? We were guessing to see if just x would work as a end behavior model. And I guessed that because it's one of these two things getting added together from my original function. That tends to be a good guess for one that's an EBM. So a right EBM, this g of x equals x, works. Now x might also work as a left end behavior model. Okay? I'm not going to work out the math on that, but it doesn't work out. if you try and do it with negative infinity. And because we're kind of running out of time here, I'll just let you know that the left EBM for this one ends up being g of x equals e to the negative x. So like I said, those two pieces tend to be pretty good guesses, and in this case it works out where those are the two end behavior models that we have for this thing. Okay. In your homework, you're going to have a chance to wrestle with this a little bit more, okay? But I didn't have time to get into it any more detail than that, unfortunately. So, all right.